Alright, CNT140, we are working on Chapter 5 on optical fiber. Some of this will be review of concepts we hit before, but some of this we're going to be adding to what we've talked about before. So let's dig in. So first thing they remind us about fiber optic, we have the core and the cladding. The core is carrying the light signal. The cladding is there to kind of act like the goalie to keep the light in the core of the fiber. And they remind us that they're made of ultra pure glass, usually. There is some plastic fiber optic, but most of the fiber optic we're dealing with will be glass. And the core is designed to have a higher index of refraction than the cladding. And because of those two, because of the difference between the indices of refraction, as the light is traveling down the core, the cladding is going to kind of bend it or potentially reflect it back into the core to keep it in the core as it travels down the fiber. And we kind of know this phenomenon. They use this picture in the book of, if you take a pencil in a beaker of water or a jar of water or a pole down into a lake, walking pole down into a lake, it looks like the actual pole or the pencil bends, if you will. Well, that's the light bending as it goes from the air to the water. That's the result of that. While in fiber optic, as we have the signal moving down through the core of the fiber, as it hits that cladding, which is in different indices of refraction, it's going to bend back into the fiber. As you see here, this mode here bends, this one bends, and if I get it shallow enough, it's actually going to reflect off and stay into the core of the fiber. When we have that, we have what they call total internal reflection, keeping the light source in the core of the fiber. The optical fiber itself is coated with our primary buffer coating, this right here. The fibers we end up looking at in our lab room, we have the blue fiber and the orange fiber inside. That's the buffer coating you're looking for. In addition to that buffer coating to protect the glass fiber, you have the strength fibers here, which we'll talk about more later, but they're there for tensile strength. If I'm installing a fiber in conduit or whatever, I can tie onto these strength fibers so I don't do any damage to the glass fiber. You don't tie onto the jacket either because the jacket can stretch. These strength fibers are designed not to stretch, so that's what they're there for, but they're also there for protecting the buffer and the fiber and so forth. And then we also have the cable jacket out here, and that, as we'll talk about later, can have different characteristics for where it's being installed. So that's kind of reminding us of all those layers of our fiber. They also remind us about making optical fiber. Hopefully you remember earlier this semester we looked at the video of how fiber is actually made. You start with the preform, you start with the glass tube. They pump it full of gas, heat it up, and that gas kind of creates a soot on the inside of the tube. They slowly melt that tube down till you have the core and the cladding of the fiber. They take that and put it into a drawing tower. Heat it up, and as the glass comes off the end into a strand, they take that strand and pull it, and basically with gravity, and then they pull it, and that ends up becoming the fiber itself. So hopefully you remember that process. Two types of fiber, multi-mode, single mode, we've hit before, but they're giving us some additional information as we go here. These are identified by their core and cladding, core composition, but also the core cladding diameters, if you will. The core cladding diameters are expressed in microns, 1/1,000,000th of a meter, and the symbol mu m, that is actually your micrometer abbreviation. So your 50-125 is your graded index fiber. That should actually be multi-mode fiber there. I have a little typo there. Mr. Brown's going to fix that right now. There we go. And there's your 50-125 graded index multi-mode fiber, 62.5 125 step index multi-mode fiber, and the 9-125 single mode fiber. Okay, we have that really small core. We know that's the single mode fiber. Most of the fibers we're dealing with have the outside diameter of 125. That keeps at least part of this standard with connectors and devices and so forth used for terminating these fibers. Reminding us the 125 is just a little thicker than maybe a human hair, or maybe like two pieces of paper laying together, because usually a piece of paper is around like 2 to 3/1000ths of an inch. So yeah, really tiny stuff. Here's just a diagram I found over the years showing you kind of like a relationship between the 62.5 step, the 50, 125 graded, and then the single mode, trying to get you to see the difference in the core to cladding diameters and the size of. Multimode fiber has light traveling in the core in many rays called modes. The multimode fiber has a larger core overall, 50 or 125 or 50 or 62.5 microns, and that's going to support that multiple modes of light moving down the fiber. Multimode fiber is generally used with either LED light sources or a specific type of laser light source. The LED light sources are using the 850 nanometer or 13 nanometer wavelength for basic lands. And then there are some lasers, VCSEL lasers, used at 850 nanometers and also 1310 nanometers for looking at gigabit speeds and sometimes just more bandwidth, not necessarily more distance, but usually more bandwidth capability. And here's just a reminder about the two multi-mode types of fiber, the step index and the graded index, and their sizes. Single mode fiber has your tiny core, 9 micron core. This tend to be used for long distance, telephony, cable TV, that sort of thing, fiber to the home kind of thing. They're using laser light sources at 1310 nanometers and 1550 nanometers. I always like to remind you guys, when you start seeing these longer wavelengths, you're usually thinking longer distances. Okay, so usually the longer wavelengths give you longer distance capabilities with this fiber. And this then has lower loss and essentially infinite bandwidth for your single mode fiber. So as I look at my comparison here, here's your single mode fiber down here, super tiny core, and a single ray of light, single mode of light, hence the laser light source. They do also remind us about plastic optical fiber. Plastic optical fiber is getting used for audio connections, sometimes in automobiles, sometimes in aircraft, so forth. So plastic optical fiber is a larger core compared to, our multi-mode single mode. It's still, it's still rather small on the outside. So, but comparatively speaking to these, it's a larger fiber. And you have here about 200 micron diameter as your core. Step index multi-mode fiber was the first fiber design. Core is made of one type of optical material, cladding a different type. So there was an abrupt difference between those two in the indices of refraction. So as the light hit, it would bounce off and reflect, if you will. Higher attenuation, and in many cases, this was used previously, are more bandwidth and higher bandwidth links now predominantly use the graded index fiber. This was your step index here. And I found a good animation, if you will, showing these multiple modes of light and how they're literally just kind of bouncing down the fiber. And the one thing to keep in mind is they're showing all the modes of light, but that is literally one pulse sent down through the fiber. All these together is like one pulse to represent a number 1, followed by no pulse of light representing a 0. So just kind of keep that in the back of your brain. Your graded index has a variation in the composition of the glass from the core to cladding. In some cases, it's actually many layers that will slowly change the indices of refraction from the core to cladding. Sometimes it's layered on there. Here we have a lot more bandwidth. The sizes is typically 50, 125. Predominantly used now premise networks, LANs, fiber to the desk, closed circuit television, other security systems. So a lot more uses in the networks that we'd be dealing with your graded index fiber, this kind here. And because there's a slow transition from the core to cladding in the indices of refraction, the light is going to bend and stay in the core of the fiber kind of more gently, if you will. Again, here's another animation kind of showing that idea of like there's multiple layers here, slowly doing the core to cladding indices of refraction change. So it tends to bend and try to stay in the core more, not be so not bouncing off so much and being a little more abrupt. That actually helps with your modal dispersion more. Then single mode fiber, they remind us that the core is so tiny that it actually, they're showing you here kind of going from like the multi-mode core down to the single mode core. It basically ends up yielding a single ray of light moving through. And now with that single ray of light, there's less dispersion issues, so my signal can travel a greater distance with your single mode fiber. Since it's only one mode, I don't have that modal dispersion problem. I can have almost essentially infinite bandwidth. My size is typically 9 to 125. Now we're using a lot of outside plant. Fiber to the home. If you have fiber to the home, you typically have a piece of single mode fiber being terminated at the side of your house. Cable TV, municipal networks, long distance data links, utility grids, etc. being used for single mode, being used for all of that. And then just reminding us of the size down here as well. They introduced to us in this chapter bend insensitive fibers. Normally a fiber optic cable, if I bend it abruptly like this, the light literally tries to leave the core and go into the cladding. And here you're seeing this is actually a visual fault locator hooked up to this fiber, which we will use very soon. And it's sending a very strong light signal down through the fiber, and it allows you to see if there's a break or a leak in the fiber, if you will. In this case, if you just bend the fiber real sharp, all those rays can't kind of bounce around the corner, and they literally start leaking out to the cladding, and you're seeing it leaking out through the side of the cable, if you will. That's what normal fiber optic would do with a sharp bend. With bend-insensitive fiber, here's your regular fiber. With bend-insensitive fiber, they actually create a lower index trench around the core. And that is there to, again, to try to coax that light back into the core before bleeding out. And they actually have some interesting microscope pictures here showing a regular piece of multimode fiber under a microscope. So we're seeing the core and the cladding, which, by the way, we will do this very soon as well. I have a fiber optic scope that I'll have you put on different fibers to look at. But here's the core and the cladding. With the bend insensitive, there is a trench created here, an extra layer between the core and the cladding, and that's there to try to help coax it back into the fiber. If I look at a piece of single mode, here's your cladding out here, there's the core and the teeny tiny core. You see a very faint color change from the core, that layer, and then the cladding. That trench there you can see is the lighter colored section right there. So we have the cladding, that light ring, that's the trench, and then the dark circle in the middle, there's your core. So there is your single mode fiber, bend insensitive single mode fiber. There are other fibers, specialty fibers. When we looked at amplifiers, fiber optic amplifiers, I believe in the last chapter, they talked about erbium doped single mode fiber being used for amplification. And then there are other fibers optimized for wavelength division multiplexing or dense wavelength division multiplexing. So there is some specialty fibers designed for special applications too. Fiber sizes, yes. As we look at single mode, multi-mode, remember our sizes. Your step index 62.5, 125, your graded index 50, 125, and then your single mode typically 9, 125. So remember your sizes there. And then also they remind us about the plastic optical fiber as well. So here's your single mode, here's your multi-mode. This is the plastic clad silica or the hard clad silica plastic fiber, and then the traditional plastic optical fiber with your basically 1,000 microns, basically a millimeter diameter here. So it's very small, but compared to the other ones, it's large. But that's your plastic optical fiber. Then the book had a couple charts here that can be used for reference on fiber sizes, looking at the capabilities of them. So these are kind of useful to remember where they are in case you need to look any of this up for its capabilities. There was the two multi-mode and the single mode. And they actually had a neat little chart in here showing kind of the family tree of fiber optic. Fiber optic is itself. Here's the multi-mode branch, single mode branch. If I look at the multi-mode branch, we see the step and the graded. And we see the step, we have these basic plastic optical fibers, if you will, now. And the graded index, this is where most of our fiber optic is that we use, including the 5125 branch and the OM2, OM3, and so forth. So that was actually a neat little way to organize all that, kind of see where they all fit in the big picture. All right, we will come back in the next podcast and continue on.